Okay. That was a starting point.
Okay, very good. Welcome to lecture 4, which will be about scattering amplitudes in quantum field theories as intersection numbers. So let me write a cartoon summary of what we've done so far. We had this original homology groups, which were the ones listed by this one form PW. We had another space which was this homology group with a similar property. And then we also introduced the complex conjugate counterparts. What we found is that there's each pairing between those objects as an interpretation. The one between homology and cohomology groups, there were computing scattering amplitudes of all strings, maybe after complex conjugation. The one between two homology groups was computing the type of amplitudes appearing in the string theory. And the thing at the bottom would be the number associated with cohomology groups. And now the question is there something more? And it turns out you can define a new cohomology group, which instead of being twisted by W, it's twisted by minus W. Okay? So that's another object in the play. And likewise, there's a bottom counterpart to this in homology. Very good. So then you can associate pairings here and there. They're not very surprising, so I won't talk about them in this talk. But there turns out to be a surprising pairing that is obtained by matching these two homology groups, one twisted with W and the other twisted with minus W. And that's what I would call a cohomology intersection number. In a sense, so cohomology, to distinguish it from the cohomology things that we computed before. So in a sense, if you ask a mathematician, they will tell you that in fact this part of the diagram is more natural than this one. So let's consider it. And the idea is that so far everything had some kind of physical interpretation. So what we would like to ask is what is the physical interpretation of this intersection number of these two cohomology classes. So first of all, let me define what it is. So intersection number of two twisted forms. Okay, so now we have two types. Let me just call them plus and minus, belonging to either this group or this group. And just to spell out what the notation is, so that we're on the same page, what I mean is homology groups of M1, and now this connection, which is plus and minus, and this is what above I call H minus P, plus minus P. Okay. So let's start with a sort of preliminary definition of the subject. So it's a bilinear between the plus and minus. To distinguish it from the objects that I had before, and to remember this twisting part, that we included as a subscript here. So our preliminary definition, after all, there's not many things that we can do, is to just take these two forms and integrate them over the full circles. Okay, but note that this definition suffers from a couple of issues. One is that naively, this phi plus, phi minus, it's a wedge of two holomorphic forms. Let me just put this here. two topomorphic forms, so that naively would vanish. Okay, so that would be a boring physical invariant which equals always 0. Fortunately, there's another issue. So there's two issues, and they will cancel out. So the other issue is that MON is non-compact. And what this means is that close to the boundary of MON, the volume diverges. So that means that we encounter sort of like a 0 to 0 problem. Okay. Then we need to regularize it. And how do we do it? Well, there's one way, which is by imposing compact support on the integrand. Let me remind you what the compact support means. It means that the integrand is supposed to vanish in the small neighborhood, or in small neighborhoods, of the boundary divisor. Okay, so how do we do it? As I said, there's a few ways, but I'm going to choose one preferred one, which is instead of this phi plus, I will consider phi plus c. And the definition of the phi plus c is that it's a form which is homologous to the original one, phi plus. So it's still an invariant between the same cohomology classes. By homologous, I mean they differ enough loud. But phi plus c will have compact support. Okay, so meaning we will vanish close to each boundary. Okay, so right off the bat, this does the same things. First of all, the away from the boundaries is just looks like phi plus c is just phi plus, so it still vanishes in the bulk of MON. So basically, the regularization didn't affect the bulk, just the boundary part of the MON, and that tells us it will be 0. Okay. Another aspect is that close to the boundary, this is imposing compact support means that phi plus c will necessarily be is non-homomorphic. Okay, and what this buys us, this implies that the full intersection number will be non-zero. Okay, because there will be some non-homomorphic pieces that can be contracted to homomorphic form. Good. So these two things together are a signal of a property called localization, which means that even though we perform the full integral over the moduli space, the integral receives contributions, non-zero contributions, only from a finite number of places, the boundary divisor. In fact, a stronger statement is true, although it's not obvious yet. extra convenience, I will introduce this normalization factor in front. And I should mention that these kind of formulas appeared before in the works of Lean and Moscow. And there was also a lot of subsequent work of Matsumoto. Okay, so they're really interesting objects. Let's compute something. And as a first example, let me consider the 4-point case. N equals 4. So this is example for N equals 4. Okay, so we call that N equals 4 in Moduli space with the CD1 minus 3 points. Okay, so with coordinates which were given by Z1 to P 4, X2, 0, so Z, 1, okay. And then for the reference, nabla in this case, plus minus, is just equal to D plus minus alpha prime S Z plus T Z minus 1 Z in this gauge fixing, in this okay. So what I will do is just construct it explicitly. I required from 5 plus C. Okay, so let me draw a picture. Okay, so the picture is we have a Z plane, which is the Moduli space coordinate. Then we have 0, 1, infinity. And what we want from our 5 plus C is that it's the same as 5 plus, but it vanishes in this sort of small epsilon neighborhoods of each 0.01. Okay, so my proposal for this designer. So clearly, we want something that differs from the original one by the total differential in nabla, and then we just construct something that goes in here. Okay. So what I'm putting here is a sum over 0, 1, infinity of the step functions. So the step functions have support inside of each circle with some radius epsilon. And they are 0 outside. And then I'm going to multiply it by the inverse of this nabla operator. Okay, good. So that's my proposal. It clearly satisfies the first condition. It's homologous to third class. And now I just need to check that this has compact support. Okay, so let's do it. There's one easy term in which that nabla hits its inverse. Okay, so that means that I will have this 5 plus from above minus the sum over P. Okay, and now I just had these two things annihilate each other. And 5 plus is already outside. So here I have a sum of the step functions. Good. And there will be a second term in which nabla is the step function. Of course, if we were mathematicians, we would do it in a smooth way, introduce a bound function, and do it that way, but for the purposes of this talk, let me do it using this approach, which means that at derivative of a step function is just a Dirac delta function. Okay, and then Dirac delta function is concentrated on these circles. Okay, so that's nice. Okay, any questions? This guy here is a 0 form or a function. Okay, so let's check if this expression has compact support. Well, clearly this is 1 minus things that are supported only here. So that means that this term is not vanishing everywhere outside of these circles. Okay, so it has compact support. The other term has only support on the delta functions, these ones. And that also means that it's compact support. So we've done our job. Good. So what we do next is just plug it in into the expression. Okay, so let's say we have two cohomologic masses, like plus, like minus, and then we want to evaluate it at 4 points. So we just do this, we copy alpha prime minus pi. Now the integral is over m4 by minus, and then wedge this expression. So in this expression, this is already holomorphic. This part is holomorphic as well. So this means that this part will not contribute. This not contribute. Okay. The only non-vanishing term would be that contracted with this term. Okay. There's minus sign. There's a sum over p. And there is the delta functions. And the inverse of this operator. That's all. That, of course, gives us a residue, and the 2 pi I factor cancels the 2 pi I factor. And we simply obtain the sum over all divisors, p0, 1s, and p, of residues around z equals p of this one form. Okay, very good. So that's the expression that we can use now. And since we've known, we've introduced some examples before of what the explicit forms can be. Let's just reuse them. Let's compute an intersection number of two Taylor forms. So just to remind you, so I'll use, this is an example, I plus minus are both Taylor forms, 1, 2, 3, 4. Okay, so this, if you evaluate it, so if you remember the definition, this is 4, 1, 4, BZ2. So that was just this part. It was just the volume, the measure form. And in the bottom, we have a chain of differences between positions of the point of Zij means Zi. So in the denominator, we'll have this chain. Permutation 1, 2, 3, 4. Okay? So that cancels with this, that cancels with this. There's a minus 1 here, and this just gives us the Z, minus Z, after plugging these expressions. intersection number of these two factorial forms. So from the definition here, we see that we have to compute the residue. And let's see how many poles this have. So this phi minus, which is the factorial form, is only poles, simple poles at z equals 0 and 1. This means that whatever this object is, we need to expand it to linear order at least in around z equals 0 and 1. And that will be enough to compute the residue. All the other terms don't matter. Okay, so let's do this computation first around z equals 0. So we need to compute this inverse operation. So let's just call this psi. Okay, psi is just the thing that we need to plug back there. Okay. Then in the next step, I'm going to move this inverse on the other side. So I just have my class, which is our original form, z, z1 minus z. And that has to be that, which was, can be copied from there. Times some function that we want to find. They just said that we need to only expand it to linear order, so we look like something like 5 plus 0, z plus 1 plus 0. Okay. So if we expand this, rounding this 0, the left-hand side will just be dz, 1 over z plus dot dot. So we let's just use the divergent term. So that's this guy. And on the other side, we have only one divergent term in around z equals 0, which is that multiplying this. Okay. This is alpha prime as z dz like 0 plus the dot. And this we can easily solve. Find that phi 0 is equal to 1 over alpha prime s. Very good. Then perhaps you can believe me that around at z equals 1, you will have an analogous computation. In fact, everything is symmetric because the pole looks the same. And the analogous computation will give you phi 1 is equal to minus 1 over alpha prime t. Very good. Now we can plug it back here. So we have this intersection number. Okay, with 4 figure forms. And then we just expanded that guy as our side. So this will give us 3 terms. The first term is the residue of 1 over z times this linear term, which just gives us alpha prime of s. The other residue gives us minus, because the residue of that is minus 1. Well, minus 1 over alpha prime t. And the residue around infinity gives us 0. Okay? So the final answer is simply 1 over s plus 1 over t. And that's the value of this intersection number. So there are 2 observations. One is that this is a 3-level amplitude of planar amplitude of the phi 2 theory. And the other observation is is that even though there were alpha primes in some places, overall as well, they all cancelled out. So final result is alpha prime independent. This will turn out to be very important. Very good. So let me just give you one other example, just to gain some intuition about how these objects look like. So this other example is following exactly the same derivation. We can compute an intersection number of just the measure form, and this combination let's say null squared. So essentially what I've done is moved one powers of denominators from left to right. Okay? And if you actually compute this, it gives you the following answer: 1 over s plus this term, and then 1 over t plus this similar term, plus 0 from infinity. And that you might recognize as again, a planar amplitude. The massive, this was masses. And this is massive. Amplitude theory with a mass one over alpha prime. So, based on these two examples, okay, the structure is roughly the following. If you increase the number of poles, you get more massive poles in the kinematic space. But likewise, if you don't have any poles, for example, these two guys didn't have any poles at infinity, these guys, we get a 0. So let me comment on the general structure of these intersection vectors. Which is hopefully motivated by these examples, is that in general, phi minus plus this are rational functions of understanding variance, so pi and pi, as well as alpha prime, with a finite number of single poles of the type 1 over some momentum squared plus an integer multitude of 1 over alpha prime. And the key point here is the word finite. Because functions with a finite number of poles are a signature of quantum field theory as opposed to string theory. So that leads us to a proposal that these objects, so physical interpretation, these objects should be as scattering amplitudes, or tree-level scattering amplitudes, in a quantum field theory, whether Okay, very good. So the next step, let me give you more motivation for this physical interpretation, which is so further evidence from this claim. And the evidence is as follows. We can consider the limit, or you can show the following result, that we consider the limit when alpha prime is 0 from a string theory integral defined by our permutation alpha as before, and some form phi class, and so. So that's, just to remind you, this is open string amplitude. You can show, and I will skip the derivation, that this coincides with a limit, the same limit of the intersection number, where instead of d of alpha, you plug in this Taylor form. And just to everyone is on the same page, this is looking like this. Okay, so from this exercise, you conclude that low energy limits of string theory, and you can show a similar result for no strings, although I won't mention it now. Coincides low energy limits of string amplitudes and intersection numbers coincide. And of course, what we expect to find in the low energy limit of string theory is a quantum field theory, and therefore that's further evidence of this conjecture. And in fact, we can give the following list of examples in which an even stronger result happens. And these examples are, if you compute an intersection number of a Taylor form with, on this phi color, which is defined over there. Okay, so it's just a linear combination of Taylor factors with some traces of color structures, and then computes, say, another copy of phi color. Okay, these turn out to be scattering amplitudes in the so-called biased scalar theory. So it's some generalization of a cubic scalar massless, which has now two color groups. Second option is that you can take your phi color, and then on the other side, you put phi gauge, again defined as over there. Okay, and these turn out to be basically the derivations of this flavor, having amplitudes in diagonal theory. And finally, to complete the table, you find that if you now put gauge on both sides, one with tilde as before, and compute the intersection number of that is now something with two polarization structures, and in fact computes scattering amplitudes in pure gravity theory. let me notice that all of these examples, and in fact, one of those guys we've seen already was like 1 over S plus 1 over T. All of them happen to be alpha prime independent. Which is quite disapparently known, but can be true. Okay, very good. So at this stage, to make connection with something that we've seen in the scattering amplitudes literature before, let me study the opposite limit.
Question?
Let's study, yes?
So is this pure gravity or gravity with a dilaton?
Gravity will be the effect. You can symmetrize the polarizations to extract the pure gravity. But now, let's study the opposite limit. So alpha prime going to infinity of intersection numbers. Well, why would you do that? Well, first of all, it's interesting to see what happens here, because we have something which is alpha prime independent to begin with. So clearly, taking alpha prime to infinity or to 0, doesn't matter which way you do it, you get the same result. So whatever we find in this, it would be a different representation of the same object, but perhaps in some more surprising way. So to do this, before we do it in the full generality, let's just stick with example at n equals 4. Okay, so for n equals 4, what we found is that this phi minus, phi plus, can be written as alpha prime, sum over all poles, residue, z equals 3. Like this. But now we want to study the asymptotics when alpha prime goes to infinity, so we can expand the only alpha prime dependencies here. So the W inverse is like 1 over this D plus the W inverse. And then let me reinstate the alpha prime here to make it more sparse with something. So the leading order in alpha prime going to infinity, this term dominates, and that form, and that thing just looks like 1 over d W plus order of the prime to the 0, to the minus 2. Okay, that's just asymptotics. Okay, so let's just plug it in here. Let's see what happens. First of all, this alpha prime cancels this one, and then you get the sum of e 0, 1, infinity, residues around the same places, and now we have phi minus, phi plus, divided by dw, plus dot dot dot, which are the subleading corrections. So let me notice one other thing, that now what we're computing is in the z-plane, we have residues around 0, 1, infinity, computed like this. But one special thing happened when you started expanding around infinity, is that you got another pole. Okay? So there's another pole here, somewhere, which comes from solving dw is equal to 0. And these things would be what we call critical point conditions. So they determine critical points of the e to the dynamic function. Okay? So now we have this other pole. Another thing that happens is that all terms here, every term in the sum, they're the same. And that means that now we can start the following decoupler, and instead of doing these residues, we can just do a single one, which is that one, with the opposite orientation. Okay, so we get minus. Now sum becomes a single term, and the single term is just a residue. Let me call this z star sum position, and we get z equals z star of again. Okay. And if I take the limit, this is the leading term. In particular, this behaves like alpha prime to the 0. So in principle, there could have been other corrections. But you see that since we know the final result is supposed to be alpha prime independent from massless quantitative pairs. And that means that this result is in fact exact. So in principle, there could be corrections that go in that one alpha prime, but they disappear from massless quantitative pairs. So now, in order to make a throwback to what we discussed in the very first lecture, let us consider generalization of that. What I mean is arbitrary n now. Okay, and that is going to use Morse function, its height function, which is the real part of W, the power potential. Okay, the Morse function is to be real. Okay, so this thing has critical points. Determined by the constraint that the derivative of this function is to be 0. Strictly speaking, is the derivative of this function, but you can show that the critical points of the holomorphic function and its real value are the same. Very good. So now you can ask, well, how many? In this case, it seemed that we had 1. So how does it generalize? And in order to prove what's the general number, let me use a complex version of a Morse lemma, which tells you that a function can be always expanded. So let me say I have some critical point somewhere, and I wanted to expand in local coordinates, and let me choose local coordinates such that the critical point is at the origin. So local coordinates against W2, W3, W2, such that critical point is at the origin. Okay, so in these coordinates, there will be some value of this critical function at the origin, and there will be some corrections. And because it's a critical point, the first correction will be quadratic. Okay, any questions? And now, this was a holomorphic coordinate, so let me just plug in its real decomposition. X and Y coordinates, which are now parameterizing the real manifold, which is the MON. Or we treat MON as a real manifold. Okay, so So how does it look like? Well, this guy will still be value of 0. And now we have plus, we plug this stuff in, and we have xj squared, and then minus yj squared from the I. And the cross term is twice 2i xj yj. Plus the dot. But we're not interested in the potential function itself. We're interested in the real value of its potential. Real value of that. Okay? So that's going to be real of w evaluated at 0. Plus real value of that. So this complex term will drop out. And that tells us something very useful, which is that locally, the Morse function looks like it has exactly n minus 3 positive directions and exactly n minus 3 negative directions. Okay, so this means it's exactly n minus 3 upwards directions and exactly n minus 3 downwards. And before that, in the first lecture, we called this quantity Morse index. Morse index of the number of downward directions. In this case, it's n minus 3. Okay. So then we can use our result that the Euler characteristic of n of n is equal to the alternating sum of n gamma on the board, where n gamma is the number of critical points with an index gamma. We just showed that all critical points have the same Morse index. And that means that there's only one term surviving here, which is minus 1 to the n minus 3 factorial times the number of critical points. So now we know how many of them we have, because we know what the Euler characteristic is, and that tells us that the number of critical points is n minus 3 factorial. If the function is sufficiently generic. Okay. So in the last 5 minutes, let's put this to use. So what we found is that there's some from each critical point, which I will now from now on call z of alpha, z of I, alpha, and alpha is 1, and next terminal. Okay. There's some submanifold that extends in the upward directions. So let me call this k of alpha. And this one that extends to the downward directions. Let me call this j of alpha. And what I will do is take my intersection number and now employ our old trick by inserting a resolution of identity in the space of cycles. But now, unlike in the case, we'll use these cycles to be the basis. Okay? So on the one side, we'll use k of alphas as the basis of homology. We'll have the intersection matrix of these two guys. And on the other side, we insert j of alpha. Okay? Well, one thing to notice is that since h alpha beta is just the intersection of j alpha and k beta, j and k, the ones that pass through the same critical point, will intersect exactly once, and the ones that pass different critical points intersect exactly 0 times. Therefore, that matrix is an identity matrix. Okay, so this simplifies, and we obtain a single sum over alpha, which goes from 1 to n raised to factorial. Integral k alpha going from here to there, e to the minus w, I minus, and integral of j alpha of e to the plus w, by plus. And crucially, with this choice, because the downwards flow are the ones where the integral converges the most, both of these intervals for each alpha all converge. In fact, converge maximum. Converge the fastest that we can. Okay, and that means we can start employing a standard point approximation, sending alpha prime going to infinity on this object. And let me remind you, alpha prime was here. That's the only place. So that means on the left hand side, we'll get the same sum, alpha going from 1 to n raised to factorial. This will localize on each solid point, so e to the minus alpha w, and the whole thing will be evaluated for each zi is equal to its value at the corresponding critical point. Okay? And there will be, after some factors of pi that we neglect, this is minus the determinant of the Hessian matrix. And then phi minus. Similarly, from the second family of loops, we'll get the exponential factor, which is the exact opposite of this one, phi plus, and then a similar ratio. So now what happens is that this and that exponential cancel out exactly, and these two square roots combine to form a single determinant. And if you do it carefully, you will find that the overall factor should have been minus 1 in this power. With this sum, and let me introduce the notation for a stripped form. So if I wanted to strip the overall differential, so I would introduce a cut. So this is a form, this is a function. So I should have put a cut. Right? Okay, so the result is phi minus hat, phi plus hat, divided by the determinant plus the dot. But as before, if you consider scattering of massless contributories, there is no corrections whatsoever, and this is the exact result. And the reason why this is interesting is that that formula was found a couple of years ago. Kachaza, Songhe, and Yuan, in almost exactly the same context. So here we managed to derive it and show its equivalence to the low energy limit of the string theory. Okay, so finish here.
The fact that it was equivalent to the low energy limit is, I mean, that there's one tiny extra step, right? Because you're not actually, the thing which is alpha prime independent is not the string amp. Obviously, it's not the string amp. It's this thing where you pair the alpha and minus alpha.
Yeah.
So you have to further argue why that thing is the same as the string amplitude as alpha prime goes to 0. Only as alpha prime goes to 0. Yeah.
Let me recap. So we found these objects intersection matters. And in general, there's some rational functions with poles of this type. alpha prime is a Z and alpha prime. In particular, for massless conductive pairs, you would not have the mass here, so the result would be independent of alpha prime. Okay. Then, separately, even more generally, what we can show is that alpha prime going to zero limit of that thing coincides with the low energy limit of string theory.
That's the step that,
I didn't show it, maybe that's why it's surprising. Oh, I skipped the duration. But this is true no matter what, even if you have these terms here. There's a second result, which also happens no matter what, even if you have passive also, which is the equivalence to this scattering
right.
equations. Okay. And then you can ask, well, when is this equal to that? And the answer to this question is when the original intersection number was independent of alpha prime to begin with. Or at least that's one solution to this question. And we know that this happens for Yang-Mills theory, gravity, and so on. And therefore, the two limits are equal in this case.
No, so I'm just saying that what's the conceptual reason for the top equivalence? Because the thing which is super clean is what you explained, is that there is something that's independent of alpha prime, you evaluate it in two limits, you get the same answer. Great.
There's a theorem. There's a theorem. I don't know what to tell you. There's a derivation in which you can show this. I don't think there's any, right now, any conceptual reason why this could be the case.
How general is the statement? Like, I mean, can you make such a statement? How much did it rely on the fact that you're dealing with M0N? I mean, good question. So this that part is fine. I'm interested in that. Yeah,
that
part.
Most
yeah.
likely, I would expect that it generalizes, but we'll have to go through the derivation and see which steps generalize and which perhaps don't. But I wouldn't be surprised if it was the case for general sort of varieties in which you have some CP1, one is some set of higher surfaces. In those cases, I think it's likely that this is still true.
It's not some like, is it easy to see that, well, maybe the simplest thing would be, is it obvious that it has poles in the same places? I mean, presumably, it should be pretty obvious that it has poles in the same places, and that, given that M0N factorizes, that the factorization properties of the rational, of this rational function should be the same, or something like that.
That would be one way. So in a sense, yeah, factorization was more or less fixed by this argument that I showed before, that the mass spectrally is always quantized. So this sort of guarantees that, with this result, this sort of guarantees that all the channels have to be at these positions. And maybe you can use it to argue.
I just meant massless factorization, even factorization on the massless poles.
Oh.
Yeah.
Yeah, that's possible.
Right.
Yes.
Any other questions for Sebastian before we take our final break? All right, if not, we'll meet back at 4:30. The last one's gone. Plus epsilon, 4:30 plus epsilon. And then we'll clap a lot.
Then even the audience is exhausted. I can't clap anymore.
Right.
PDF for the schedule for this conference. It's called Spacetime schedule PDF. I don't know why.
I just saw your paper. I saw your paper.
Oh, yes, instead of looking at the talk.
Yeah, it does say
I may be answering the question.
every lecture is an end.
Oh, yeah, sorry.
Context.